Okay, so welcome back. Example number one from chapter 8. Again, this is a chapter discussing confidence intervals. And be careful with these questions because chapters 7, 8, and 9 often blend into each other. And so make sure you read the questions very carefully on the exam in order to determine really what they're asking for. So without further ado, let's jump in. Suppose that an independent laboratory has tested trash bags and has found that no 30-gallon bags that are currently available on the market have a mean breaking strength of 50 pounds or more. So no bag on the market really can hold more than 50 pounds. On the basis of these results, the producer of a new improved trash bag feels sure, this is a key thing, feels sure that its 30-pound bags, 30-gallon bags, will be the strongest such bag on the market if the new trash bag's mean breaking strength can be shown to be at least 50 pounds. So this is a version of a chapter 9 problem that begins with a claim. So this producer feels that their bag will be the strongest if they can prove that it can hold more than 50 pounds or 50 pounds or more. So they took a sample, and this should be a big tip-off right here. So n is equal to 40. And immediately when we see samples, you're going to start thinking, okay, do I need to use the z value or the t value to solve this problem? So the question is z versus t. In this particular case, n is greater than 30, so we're going to use z. The other reason why we would use z is if sigma is known. So if sigma is known, then again, we use z. In the case where sigma is unknown, we would still use z because n is greater than 40. So we could kind of cheat. Or you can use t if you like. You would still not be completely wrong. Now, if this was a written problem, obviously there's a little bit more wiggle room. On the exam, you have to be very careful what you choose. I would say go ahead with T just to be more conservative, but do your question twice, check it out, one versus the other. The answer should be very close, and then see which of the answers given matches your answer. So that's your choice. If sigma is unknown and your sample size is less than 30, let's say 20, then obviously you always use t. There's no question about that. So let's take these out here. Continue the problem. So they took a sample of 40 and the result was that the average was 50.575. For someone who doesn't know statistics, they would say, well, hey, that's enough evidence. But no, this could have just been a result of a random sample. Maybe the sample they've taken was for some reason extra strong. But that's not indicative that that's the case for the entire population. So there's your average, 50.57. And they go ahead and tell us that the standard deviation of the population is actually 1.65. So life is great. We have a combination of two variables here that tell us that we should use the z value. So there is no question about what we need to do. Question number A, or part A, it says calculate the 95 and 99% confidence intervals for mu. So let's go ahead and do that. The first one I'll do a little bit more in detail. The next one I'll go in much quickly. So the formula, x bar plus or minus z alpha divided by 2 sigma over the square root of n. Remember, this is called your margin of error, sometimes abbreviated as E. Okay, so 50.575 plus or minus, we need the standard normal value here. Remember, what you're looking for is z 5% divided by 2. Now, why is that 5%? Because 1 minus alpha is going to equal 95%, and so alpha has to be a 5%. So you're looking for 5% in the tail. And what I mean by that, for those of you who may have just heard this for the first time, if this is your distribution, you've got your center here, your mean, and you've got your cutoff marks. This part and this part, the remaining parts are going to be alpha divided by 2, which in this case is 5% divided by 2, which is 2.5%. And it's the same thing on the other side. And because that's 2.5% in that tail. The entire region, you know, is 50%, which leaves us with 47.5% here, and it's symmetrical, so it's the same thing on this side. So when I look up values in the Z table, I'm going to look up 47.5%. Let's clean that up. Go to my Z table, it's right here. I'm looking up 47.5. In this particularly lucky case, we have an exact value right there. That's fine. And so all I need to do now is look up its Z value. So on the vertical, I have 1.9. On the horizontal, I have 1.9. On the vertical, I have 0.06. So together, that's 1.96. That is my standard normal value. Just go ahead and put it in red, 1.96. And then the rest of the problem is simply plug and play. And I calculated the margin of error as 0.509. Check my math just in case, which gives me a confidence interval that looks like this. So obviously the center is going to be 50.575. The upper limit is going to be 51.086, and the lower limit is going to be 50.064. Okay, so that is your confidence interval at the 99% confidence level. You are 95% confident that the real average of the population, and remember that real average is called mu, you are 95% sure that it is here, 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 somewhere within this interval. There is a 5% chance that it could be somewhere here or here. So I'm going to clean up here. I'm going to keep the confidence interval because we need it for the next problem. And so the second part of that problem says, give me the 99% confidence interval. So what we have is 50.057, 50.575 plus or minus, I need the Z1 divided by 2 standard normal value. In this particular case, I'm looking for 50 minus 1 divided by 2, 1% divided by 2, which gives me 49.5%. Okay, so one more time, in terms of the illustration, here is my center. This side and this side are both going to be 1 divided by 2. Let's clarify just a little bit. 1% divided by 2, so that's half of a percent, 0.05%. And know that the whole thing is 50%, so this is here 49.5%. Okay, same thing on the other side. No need to worry about that. I look up 49.5 in my table. This is another particular case because 49.5 is not available. Under other circumstances, all you need to do is take the closest value. But in this particular case, you should take the average because it is exactly the two values that we see are both exactly the same distance away from the value we're looking for. So in this particular case, you can find the Z value for both of them. 2.5 and then 2.57 on the vertical, and then for this one it's 2.5 and 0.08 on the vertical. So what that tells us, or what we can do there, is 2.57 plus 2.58 divided by 2, 2.575. That is your Z value that you need to use. $2.575, 1.65 standard deviation of the population divided by 40 is the sample size, 50.575 plus or minus, and I have 0.669. Obviously, the margin of error is much larger when it comes to a larger confidence interval. And so if we're building this we would have 50.575. The upper limit is going to be 51,247. And then the lower limit will be 49.903. So it is with 99% confidence that we believe the real average is somewhere between 51.247 and 49.903. I'm going to keep both of these. We're going to need them, but I will move them up. And I'm aligning them for a particular reason. Just make them aligned. Perfect. Okay, so the next problem, actually both of the C and D are very similar. It says using the 99% confidence interval, can we be 99% confident that the mu is at least 50 pounds? And for B, use 95% confidence interval, can we be 95% confident that mu is at least 50 pounds? So both of the same question, except one uses 95, one uses 99. So are we sure on the 95% level? And what about the 99% level? Well, let's look at it. At the 95% level, let's write 50. 50 is actually lower than 50.064, obviously. And so let's write it here. And so we could see that it is outside the interval, meaning all the evidence shows that the average weight of the population is actually much larger than 50. It's greater than 50 because the lower limit is actually 50.064. So with 95% confidence, we can say, yes, we believe that the strength of the new bag is greater than 50 pounds. Now at the 99% confidence level, things change because you could see that 50 actually falls within the confidence interval. Because it falls within the confidence interval, we cannot be sure that the strength of the bags is greater than 50 because obviously the bags could weigh or could hold 49.9 pounds, which is less than what we want. And so this is a possibility. And because it's less than 50, then we can't really be sure. So at the 99% confidence, no, the answer is we are not confident that the strength of the bags is at least 50 pounds or more. Based on your answers to part B and C, how convinced are you that the new 30-gallon trash bags is the strongest bag on the market? Well, you're kind of 50-50. I say that off the cuff remark, it's not actually calculated as 50-50, but you're essentially not sure because you have conflicting evidence. At the 95% confidence level, you say yes. At the 99, you say no. So it is not a clear-cut case in this particular situation. So it's up in the air. So this leads us to part E. You want to be more precise. You would like to be a little bit more accurate. And so you're asked to calculate the sample size needed to calculate the 99% confidence interval to within 0.5 pounds. What sample size do you need in order to be that confident? Well, just kind of a small reminder, what you're trying to do with these sample size problems is essentially you have your problem here or your formula for your confidence interval. You have to understand that this is your E, you're taking your E and you're saying, you know what, solve it such that it is equal to 0.05, or in this case, 0.5. So we're going to set that equal to 0.5, and that means the other side has to equal to 0.5 as well. And so what we try to do is we solve for n. So n is equal to z alpha divided by 2 sigma over e squared. Plug and play, nothing easier than that. So let's go ahead and do that. So we're using the 99% confidence level. So we're going to use the same z-score, so 2.575 multiplied by the standard deviation of the population, 1.65, divided by the margin of error that we need. So this is the within half of a pound, and just square and you get. And always check my math. My numbers say I should have 72.2075. That is a horrible looking 7. Now, this is the exact number that you need to sample in order to get the precision that you want. That is a mixed number, which you cannot do when you are dealing with discrete observations. So in this particular case, always round up. So you need 73 sample size of 73 in order to be that precise. So what that means is then you will basically be able to create a confidence interval that looks like this. Your middle here, 50.575. You're going to add 0.5 to this side, and you're going to add or subtract 0.5 to this side. And you will be 99% confident that your real mu is here, here, or here, somewhere.